morning, everybody, and welcome to this year's Faculty of Engineering and Technology Research Week. I'd like to introduce Professor Jin Wang, who will open the proceedings this morning.
Thank you, Mr. Chairman. Good morning, everybody. It's such a good day to have Research Week from today, sunny and warm. We can't have a better day to start our research event than today. I open the conference now. Good morning, everybody. It's my pleasure to welcome you all to the opening of the Postgraduate Research Conference of the Faculty of Engineering and Technology this year. It is an exciting time for the faculty as we continue to grow and adapt, remaining always adaptable, motivated, responsive, application-focused, and open to new ideas. We'll continue to bring inspired researchers together in forums like this to ensure that our research remains at the cutting edge. This is our faculty's second postgraduate research conference, providing our PhD researchers with an opportunity of presenting the research findings and sharing their research experience. For many years, our research institutes and research centers have organized the annual conferences individually. And this year, I'm delighted to see that all the research centers and institutes within the faculty have worked together again to have this year's research conference. Engineering and technology has penetrated into virtually all areas in everyday life, ranging from computer security to health monitoring and diagnosis, from car manufacturing to maritime logistics, and from alternative energy generation to built environment. To effectively benefit from engineering and technology applications, it is essential that researchers share their findings and their research experience so as to set themselves ready for transforming their practices and keep identifying effective ways for transformation in their contexts. If you look at this year's conference program, you will agree that the conference is going to be busy and productive. There is a lot of activity to offer for the 5-day event. I would like to give you an idea of what you can expect and what we hope to achieve over the next 5 days. There will be 5 keynote addresses, more than 90 oral and 50 poster presentations. There will be awards for the best papers, best posters, best elevator pitches, and best presentations. So in total, there will be 12 awards. For every category, there will be the first award, second award, and third award activities. Throughout this conference, I ask you to stay engaged, keep us proactive, and help us shape the future of the faculty's research. In closing, I hope that all of you will enjoy the conference. Thank you for your attention. We can start the research conference now. I pass the responsibilities to the conference chairman, Dr. Bill Atherton. Thank you very much.
It's my pleasure to introduce our first speaker today, which is our keynote speaker, which is Dr. Anton Popov. He is the Associate Professor of Department of Physical and Biomedical Electronics from the National Technical University of Ukraine. He is head of the Biomedical and Electronics and Signal Analysis Group. He received his PhD in 2007, and so far he has published more than 30 peer-reviewed journal papers and has published one book. He has many research interests, and he is a senior member of the IEEE and chairman of the IEEE in Ukraine in engineering, medicine and biology. And I'd like to welcome him this morning as he gives us his talk, which is related to biomedical signal analysis, the evaluation of human functional state.
Thank you, Mr. Chairman. Thank you, Professor Won, for such a nice introduction and opening address. This is the outline of my talk today. First, I will give a short introduction of where I came from, some words about my university. Then I will switch to the Internet of Things medical product paradigm as we see it. And then I will present some examples and some results of what we are doing in this field. First of all, I came here from Ukraine. This is a country between Russia and Poland, near the Black Sea. I live founded in 1898, and when talking about history of our university, we're proud that Professor Dmitry Mendeleev, who invented the periodic table of elements, was the chairman of the very, very first examination board. He's here sitting and listening to first students. Also, Sergei Korolev, who is the inventor of the spaceships, was also our student. And Igor Sikorsky, who invented the helicopter, also studied in Kyiv Polytechnical Institute. I am from Faculty of Electronics, which was established in 1962. Now we have a bit more than 1,500 of students at different levels. We have approximately 150 faculty staff, and there are 7 departments in our faculty. I am personally from the Department of Physical Biomedical Electronics. We also have departments which work in acoustics, acoustic electronics, electronic device, plasma techniques, telecommunication, etc., etc. And also we have a research institute affiliated with our faculty, which is called Institute of Applied Electronics. This is a campus map. We have 2 buildings, a building for lectures and the laboratory building, all in the same campus with beautiful shady park, very, very close to it. And this older meter is also situated very close, so we are a very compact campus, almost in the center of the city. We have now 3 programs, academic programs in our faculty at bachelor and master level: micro nano system engineering, electronics, and telecommunications and radio engineering. And we have 7 PhD programs, which we are changing right now according to the new directions, new trends. And personally, I work for this program biological and medical instruments and systems. And just a few words about my department. We were founded in 1974 by Professor Vitaly Sigorsky, who was a researcher in the area of circuit theory, matrix analysis of electronic circuits in simulation of transistors, etc. And we work for this bachelor program, micro nano electronics, biomedical devices, microwave, etc. And there are several research groups in my department. Microwave electronics, the group for studying interaction between physical fields and living objects. And one of these groups is my group. It's called Biomedical Electronics and Signal Analysis Group. And what we do, we are focused on the 4 areas. We measure, process, analyze, and interpret all parameters which could be measured from living objects, and we are doing that for finding some useful information which could be provided to medical doctors to treat patients better, actually. So the three main areas of my group is applied fundamental R&D in biomedical engineering, data processing and analysis algorithms, and also hardware, firmware development for biomedical electronics. This is how we see the world of medical things, medical-related Internet of Things product system, let's say. We see here, they are very tiny, but they are very important. It's a patients, or not patients, but healthy people. And these persons are surrounded by so-called body area network of things. It's a lot of sensors. It can measure like blood pressure, temperature, EEG, heart rate, etc. It's very wearable devices like fitness trackers, some artificial organs, prosthetics, and exoskeletons, some sensors for measuring motion, pressure, steps, etc., etc. Around these persons, there are like the unit or the block of real-time patient monitoring, including personal advisory system for these guys. Also, we have in this medical product system professional medical care in hospitals with very complicated equipment, etc. We have to provide them with emergency care and alarm system. Also, we have to provide them with the home health care, which could be constantly operated whenever they are situated right now, wherever they live. Around them, there are other things network like smart home, smart cars, smart enterprise, smart shop, etc., which also should interact with them somehow. And all this should be supported by comprehensive data analytics, specific signal analysis algorithms, some exploratory or deep data analysis, etc. And everything now is happening in the cloud, so we have to provide like data warehousing for them, provide security, we have to provide a reliable connectivity, we have to be low emission, etc., etc. So all of this is medical IoT product system which exists in real world, and this is how it reflected from our point of view in so-called reference platform, the hardware, software, and in-between platform for this product system. And this is how any of those devices can be simulated, can be manufactured, can be modeled, can be implemented actually. So we have several blocks in this reference platform. First, it's of course hardware, firmware, and biosensors, the most important part, which interacts between the human being, the environment, let's say, and all the electronic equipment. So it measures the raw data and transfer it to the system. Also, we have data analytics toolbox. As I said, we have to deal with all this data flow somehow. We have to process them. We have to prepare them for further analysis. We have to explore what this data could say to us, etc. Of course, we have to provide the cloud utility. We have to store the data. We have to provide constant access to them. We should have some application, mobile or web-based. We should integrate with third-party product because we are not alone, and our system, which we develop, should interact with other systems as well. And everything here is connected by some connectivity tools, some products, platforms, and technologies. Today I'll be talking about data analytics mostly, and here is how we see this part, this second data analytics toolbox. We have here the raw data flow from biosensors coming in the system. Then we have the signal processing and analysis blocks, which could be in real world, which could be divided between the device itself, the hardware, and implemented in firmware. And also we can have some signal processing and analytics tools implemented in the cloud, for example, or in the application. After data are processed, analyzed, we have the flow of augmented data, which already contain not only raw signal data, but also some information about what is going on, some parameters, etc. And we have to be able to visualize them and store them somehow. And the most important part here, in which we are working most heavily, is this part. It's the library of some signal-specific algorithms for each type of biosignal or for some combination of biosignals, for example, for studying and analysis of brain activity, heart activity, pulse rate, steps, etc., etc. So this library of algorithms is of our main interest today. And here is what are the research areas about which I'll be talking today. So actually in our lab we work on the signals coming from many organs, many parts of the human body, from brain, eyes, muscles, lungs, heart, etc. But today I will try to share with you the results and problems we faced connected to brain activity analysis, heart activity, some respiration, and diagnosis of Alzheimer's disease. And as I said, all this could be applied in any biomedical system. There are like seven types of them for diagnosis, monitoring, life support, visualization, therapy, etc. So first I start from analysis of electroencephalogram, which is the largest topic of my lab. Some historical information. The first electroencephalogram, the first EEG, was recorded in 1875 by Richard Caton from the dogs and apes, and only like almost 50 years after that, in 1924, Hans Berger for the first time recorded the electrical activity of the brain from the human being, and he also performed heavy research on that. He reported the changes of brain activity in sleep, in hypnosis, during some pathological states, etc., etc. Here you can see the very first record of brain activity made by Hans Berger from his son, because he worked with him and tested all his devices on his son. And electroencephalogram signal is the multi-channel record of potential differences that would be registered from the head surface. There are several types of EEG, from surface itself, from the surface of cortex, which is called electrocorticogram, and there is also like possibility to measure EEG from the deep of the brain using micro electrodes. And by the way, here is the screenshot of the very first scientific paper on electroencephalogram. It was published in 22 of April in 1929. To get this signal, you have to place a lot of electrodes over the head surface and measure simultaneously all all potential differences from that, and in the result you can obtain such kind of records, multi-channel, not very high frequency. In the most research we use the signals in the frequency range from 0.1 up to 40 Hertz, so it's low frequency signal and very, very low magnitude. In normal condition, the EEG of a human is up to 100, let's say, microvolts. So the normal EEG looks like that. But we are mostly interested in the changes of brain electrical activity during epilepsy, which is a group of diseases characterized by sudden, unpredictable, and repeated seizures, which manifest by tremor, convulsions, loss of consciousness, hallucinations, screaming, etc. And the cause of epilepsy can be very different, like insult, trauma, vascular disease, inflammations, genetic inclinations, etc. And if person experiences epileptic seizure, the signal looks like this. So starting from the 45 second, we have the increase of magnitude and increase of frequency contents of the signal, and this is the sign of epileptic seizure, of brain activity during epileptic seizure. And we are mostly focused on analyzing this kind of signals. So this is another example of EEG during epileptic seizure. You see, in almost all channels, we can see very prominent, very high magnitude and quasi-periodic waveforms, which contains of high magnitude spike followed by the slow wave. And if doctor sees this kind of signal, everything is clear, the patient should be treated. But what initially the doctor wants to find in this signal is so-called epileptic oscillation complexes. These are the waveforms of different shapes, but very, very similar, let's say. When doctor sees the complex of sharp wave and followed by slow wave, this is the sign that somewhere in the brain there is some epileptic focus, and well, the patient has to be treated somehow. But if we look on this example, everything really clear, very, very clear focuses, sharp and slow wave. But at the early stage of disease, when the focus is slow, such kind of waveforms could be masked by background activity. For example, like here, there is only one small complex in only one channel, and it could be a very, very low magnitude like this compared to the background activity. And these complexes should be detected as well, because as early you detect, the early you can start the treatment. So we are focused on finding this kind of waveforms which are non-prominent, low magnitude, and of distorted shape. And we worked on this problem for like 10 years now, and we use different mathematical approach. For example, we used the template matching with adapted template for doing that. We described the possible changes of this classical canonical shape and tried to develop the template for all possibilities of changes of the form. And we implemented this and obtained quite good results, like 85% of true positive and 82% of sensitivity. That was one approach. Also, we applied the wavelet analysis for finding this kind of complexes, and we developed a technique to construct the adapted mother wavelet function. which is specially suited for the shape of the complex of the epileptiform complex we want to find. We used the Asian vector technique for that. We collected some examples of the complexes of different shapes and then developed the template by using the main eigenvector of the covariation matrix of these complexes, and then constructed a mother wavelet based on this shape. And also had quite good results. True positives were 93%. And also our partners in clinics, they said that it's quite enough for applying this to real patient, real diagnosis, let's say. A couple of years ago, we switched a bit to the epileptic seizure prediction, because before that was a detection of epileptiform event, let's say, and now we are looking into the task how to predict epileptic seizure and prevent them. And this is like the high-level presentation of how this kind of system should work. First, we have a brain, and we have signals from it. The first block should extract some features from EEG mainly, but now it's said that even heart activity changes before the epileptic seizure onset, so we have to perform some kind of data analysis. Then we might also want to study some coupling between different systems in human body, and this coupling also can change before the epileptic seizure. I will talk about this a bit later. Then we have a block which should perform classification and predict, and in the result we have the outcome of situation analysis based on optimized feature set, and we have to decide whether the seizure is closed, and if yes, we have to select the strategy for controlling the neurostimulator part and then generate the signals to stimulate the brain or some other part, some other tissues to prevent epileptic seizure. So this is what we want to do. How we started to do this? This is how the EEG before seizure is divided into parts. The part when there is actual epileptic seizure is called ictal. Preictal part is the part of signals during which we can extract some parameters which are changed substantially to give us information then that, for example, in 10 minutes, the probability of epileptic seizure is higher than 80%, for example. So this is like our prediction horizon, let's say, and interictal part, which is normal activity for the epileptic brain. Of course, it's not very normal often, but it's not preictal. So the parameters which could be extracted from this part are more or less stable and not worrying us. What we did, we used very simple feature extraction technique based on correlation analysis between all electrodes. We see the number of channels here and the different values of correlation, and we continue to work on that to try to predict the seizures using this feature. Here are our results. We constructed the patient-specific system for seizure prediction. That means that for every patient it should be trained separately, so we don't do any generalization for population. And based on our data set, we now defined the optimal time window for signal analysis which gives us the largest value of classification efficiency, let's say, the largest area under curve value is 0.97. So you see, for different patients, this parameter is different. That means that probably patient-specific strategy is correct one, and it changes also from 5 minutes up to 10 seconds. So we still work in this area. Also, we work at the estimation of coupling of connections between heart activity and brain activity, about two systems, very important, cardiovascular and central nervous system. These two systems are definitely connected physiologically, connected anatomically, and a lot of processes are inside them, and we try to analyze this connectivity and to extract some meaningful parameters which could be used for description of sleep quality assessment, anesthesia and sleep stages, and of course epileptic seizure prediction. And the main parameter which could be used for cardiovascular activity studying, it's heart rate variability, which is the phenomena of the changes between consequent heartbeats. The heart beats not periodically in healthy human. That's very good. And studying the sequences of these intervals, we can extract very nice, very interesting information. So there is a lot of parameters here. There is a standard used and adopted everywhere. We have time domain analysis, frequency, etc. But we are only at the start. So this mutual information measure between heart and brain activity, this plot might look not very, very good. But it's our first result, not the best. But here you see 0 time point corresponds to the start of a seizure, and this part is the result of mutual information estimation between high frequency power for cardiovascular, for heart rate, and full power of brain electrical activity. And we work for defining the parameter which could be substantially different between during interictal, let's say, part and pre-ictal part, somewhere like this, this one and that. You see, in 5 minutes before seizure, this box plot is much lower than all box plots before that. So hopefully we'll find a measure which will change, which will change before this seizure. We also work on the characterization of heart activity before the epileptic seizure and during epileptic seizure with our colleagues from Children Epilepsy Clinic in Kiev. And this is an example of some measure. It's the determination parameter for recurrent plots. This is nonlinear technique of analysis of numerical sequences, and also we see that here the epileptic seizure started, and there is substantial differences between the values of this parameter during the seizure, after the seizure, and before the seizure. It also might have might bring some new information about how heart activity changes in epilepsy and during epileptic seizure. We also worked on the heart activity analysis during sleep, to do sleep studies and sleep staging. Now the standard says that to evaluate sleep quality, you have to measure at least 3 signals. It's brain electrical activity, EEG, electroculography, and the electromyography from the chin. But we know that during sleep, heart activity also changes, and we have high parasympathetic activity. We have lowering of sympathetic activity. We have the increase of respiratory sinus arrhythmia during sleep. So, together with our colleagues from Dresden Technical University, we try to do sleep staging, not using the EEG brain activity as now it's widely adopted, but using the heart activity, using some parameters extracted from heart rate variability. And this is our pipeline. So we extract, we measure EEG, of course, we measure heart activity during sleep. Then we try to find some parameters, some features which are coupled the most, which are connected to each other from brain and heart. Then we estimate the quality, and in this way we can define which characteristic of heart activity could be used to estimate sleep stages, to estimate the sleep quality, etc. And we are focusing mostly on nonlinear methods, such as phase locking values, transfer entropy, some cross-spectral and cross-spectral Bayesian analysis, causality measures, etc., etc. And we try different techniques to connect them somehow. So this is also the ongoing project, let's say. Also, we have a small group which works on ECG solely, and they do some very interesting research on the detection of fetus heart rate, because it's known that some heart diseases in children, even in fetus, could be detected as early as after 2 or up to 8 weeks of pregnancy. So if we are able to measure the activity of the heart of the fetus, we can extract some parameters and we can start treatment much earlier. And my colleagues, they measured such kind of signals from abdominal leads and also from thorax lead, classical ECG from mother. And they developed the technique to extract only the heartbeats of a fetus. They are very small. They are hidden by the high frequency noise, but using the wavelet technique and adapted the composition, they managed to do that. They have removed the drift, they have adaptive filtration, and here you can see the classical ECG of a mother, but on the signal you see these tiny peaks, which are the signs of heartbeat of a fetus, and we can separate them quite good. So you can have one channel of fetal ECG, and you can analyze it, and you can try to extract some diagnostical parameters from this kind of signal. Another topic of our lab is analysis of respiration. There is a lot of applications of monitoring the breathing of a person, starting from medical, game industry, some safety applications, sport, home care, etc., etc. But we are focused on the patient monitoring and breathing support in intensive care units, together with our partners from the company which manufacture the mechanical lung ventilators. And there is quite a lot of signals, a lot of data are being measured from the person in ICU, ECG, EMG, classical one, some breathing parameters, and blood gases as well. And here is how the screen of mechanical lung ventilator looks like. You see a lot of parameters, and the doctor should take care of setting all of them manually or semi-manually. And what we do here is the study of arterial blood oxygen saturation signal, because it could be used to control the level of oxygenation in ICU. And this is an example of how it looks. I believe this is 1 day long record, and you see there are some drops in this signal. This is an enlarged part. It's very, very slow changing, and the oxygenation normally shouldn't fall below, let's say, 90%. But of course, in ICU, it happens that it can drop down substantially, and what we should do is to distinguish between the actual drop of the oxygenation and so-called false alarms, when the signal is lower than the threshold, but not for a long time. And we were asked to work on that and to propose some technique to decrease the rate of false alarms. And what we do, we also applied the adapted smoothing technique, adapted filtration in wavelet domain, and in this way we eliminate some false alarms in such kind of signals. And this, now it's also ongoing work, and we hope that we implement this in real mechanical lung ventilator device. What else we do? We also work on the contactless respiration extraction techniques. This is the example of how it's done from our colleagues from Dresden Technical University. This is the signal from, I hope it will start because it's a video. Let's try. Oh, you see. They have installed respiration, they have installed infrared camera, and they measure the pattern, the temperature distribution of the face, and they try to extract this part of nose, and they measure the intensity of the signals coming from here, and because patient breathes, the temperature changes, and they extract quite a good pattern of respiration from it. This is one approach. It requires quite expensive infrared camera. What we do, we try to extract the same, but using the regular cameras in optical domain, also to do this contactless. There are a lot of techniques to extract respiration. We use in our lab two-dimensional image processing based on optical flow measurement. And you see how we can do this. This is Oleg, my PhD student. The signal comes from the area of a chest. He breathes, and the optical flow changes. We subtract this part and extract the pattern of respiration. The signal is not very clean here, but we also use some filtration technique to remove high frequency noise from that, and also we use the geometrical methods to separate the area which actually should move during respiration, the area of a chest, and in this way we do all this job. And one more area of application of our group. This is diagnosis of Alzheimer's disease. We work on that together with our colleagues from University of Granada from Spain. Alzheimer's disease is very common now. and very widespread. And since the term of life now increases, in the same time, the amount of people who suffer Alzheimer's disease also increases. And this is the most widespread form of dementia, and there is no cure, unfortunately, for this disease. And what doctors can do, they can just ease somehow the suffering. Now, the main signs are confusion, are irritability, swings of the mood, memory loss, language loss, etc. And here you can see the comparison between the brain of normal, healthy person and persons suffering Alzheimer's disease. You see the shrinkage of the brain, the increase of cavities, and the most important that this disease affects the brains, the brain parts which are responsible for language and responsible for memory. To diagnose Alzheimer's now, they use mostly MRI, magnetic resonance imaging technique, and you see again the comparison between two brains. You see the symmetrical atrophy could be noticed, the atrophy in temporal lobe, the expansion of fissures, the expansion of the ventricular system during Alzheimer's. So now these signs, these features are the ones to be extracted from MRI. And if the patient is at the later stages of disease, when disease is very prominent, it's not hard to extract this sign just by measuring, by normalization of something. But what we are doing, we try to diagnose the early stages of Alzheimer's disease when these changes are not very prominent, when they are tiny. And what we decided to try, and we do this quite successfully, we decided to apply fuzzy logic to diagnosis of all this disease. And the reason was that since the disease itself is a very gradual process, very slow process, and the division between stages are very, very smooth and unseen, so it's not abrupt change, for example, like a stroke. Today you don't have it, and in a minute you have it. Alzheimer's disease is very continuous process. So we decided to apply this fuzzy logic technique. The main difference between fuzzy logic and classical logic is that each object can be referred to each class simultaneously, to all of the classes simultaneously, but with the different level of membership, let's say. So membership function in classical logic looks like this. So, for example, if you estimate whether the person is tall or small, you just set the threshold of height of the height of the person, and you can decide it yes or no. But in fuzzy logic, the membership function between small person and tall person looks like this. So it's gradual changes, and we can define that some person not so tall, another not so small, and we use this approach to Alzheimer's disease. So it's like normal brain, Alzheimer's disease brain, and something in between. What we do, we construct fuzzy inference system for that. We use several modalities of measurement for diagnosis, not only magnetic resonance imaging, but also the positron emission imaging. The main blocks are preprocessing, normalization, spatial, and segmentation of MRI features, and then feature extraction and fuzzy inference. And you can see here our results. This is binary classification now. So for example, the most important here is classification between normal and mild cognitive impairment, which is the state of like in between normal and Alzheimer. So we believe that this could be treated like an early stage. And you see that the positive predictive value is 0.84, which is not bad. And this result was recently published in current Alzheimer diagnosis journal. So we continue to work in that direction. Also, we have the technique to estimate the importance of different brain regions for using as a features for Alzheimer's disease diagnosis. This is an example of the results. So you see in red, we highlighted the regions which differ substantially between Alzheimer's and normal brain. So that's actually almost all. I just would like to mention the list of our partners here. Two companies, UTAS, which manufacture biomedical devices in Ukraine. It's the largest manufacturer there. And Cyclum company, which is our technological partners in software hardware development. Also a lot of departments, institutes, medical, etc. I sincerely hope that your university also could be mentioned here. We would be proud to work with you if the areas are close, hopefully. And of course, actually, these guys do all job. This is our group, our students, bachelor, master, PhDs. All these results obtained by them. Also, I would like to mention that my visit here was supported by British Council by exploratory visit grant, and I am grateful for that opportunity. And also, I am very grateful for inviting me here to Dr. Olga Korostynska and her group here. And that's all. Thank you very much for your attention. I hope it was not boring. Thanks. Thank you.
Can we take questions from the audience, please, for Anton? Please.
Thank you very much for this interesting presentation. Much of your work you're doing here, also doing with the computer department, with the applied computing research group, which I'm leading. We have also a number of PhD students. But what we try to do is actually to look at the artificial intelligence and machine learning for doing lots of those predictions. Do you also use that for your lab?
Yes, sure. We heavily use machine learning approach, starting from this fuzzy inference system. We use some classifiers, binary and multi-class classification technique. So definitely we use it. We use feature extraction, feature selection, feature reduction, etc. So it would definitely we do that.
Please.
In terms of feature extraction, do you actually use summary statistics on a particular interval of the EEG, or do you move to machine learning-based methods as well?
We actually do more machine learning, and we treat our signal like a part of the whole record, and we try to extract some features from this part. But these features could also be statistical. For example, the moments, the distributions, etc.
So in terms of machine learning, can you give an example of which particular features you get extracted from the got bandwidth and things like that?
For example, in
Can you give an alternative non-conventional feature that you've extracted?
For example, when we try to predict epileptic seizure, this result were not shown here. We use the entropy characteristics. We use approximate entropy, sample entropy, and then we, along with some other techniques, along with the distribution moments, and we supply them to the SVM classifier.
So the actual the features are assumed prior, and they're based on statistical measures, and the static calculation is done, and then they're fed into the machine learning at the end of this. They've not actually applied machine learning to the raw signal as such. Am I correct in saying this one?
Yes, if I understand you right, we select the features, then we use classification, and then we estimate if these features are effective enough. If not, we change either classifier or feature set.
Please.
One of the slides, we have seen that you use the MRI images and you have selected the affected area in the MRI images. I'm sorry. And in one of the slides, I have seen actually you use the MRI and you have selected the affected area in this MRI. Actually, what technique you have used to just highlight this area? Is that actually done visually, or there is actually an artificial intelligence technique to do this process?
Mhm. We used a t-test based technique. We have an atlas of brain functional and anatomical regions, and we have a set of MRI images from the ADNI database, and we try to find which areas, based on the atlas, which areas are most distinctive, which areas most different between healthy brain and Alzheimer's disease brain. We use the intensity of voxels in these areas, and we use the t-test to compare. If they are different, we use p-value as an indicator to rank features, to rank the areas actually. If the t-test shows that they are very different with very small p-value, we think that in these regions, the brain tissue differs, and we can extract the features from this region to supply them to the classifier. So we use t-test based selection of regions.
Can I contact you in the future just for more details about this?
Yeah, sure, we can talk about it.
Please.
Hi, my friend. Thanks very much for your presentation. I know you're working with signals, but do you work also with genetic data by any chance?
No, unfortunately, no.
Thanks.
Are there any other questions for Anton, please? Anton, I have one. Where do you see the future of this work going in terms of things like wireless sensors for early prediction of seizures, particularly in vulnerable people, people living on their own, where information could perhaps be sent to a mobile phone or a smartphone?
Mhm.
Do you
Thank
see
you.
that?
Well, of course, we want to develop such kind of system which could be wearable and could be convenient to wear. And that's why one very important question, one very important task in this seizure prediction based on EEG, for example, is to reduce the number of channels which should be measured.
Mm-hmm.
Because now we use full set of channels. It's at least 19 channels placed all over the head, and it's definitely not very useful. So we want to reduce it to 1 or 2, for example. And that's why we try to extract the features to predict epileptic seizure from heart activity, because it's definitely much more easier to measure, and each fitness tracker can measure your heartbeats. And we hope that based on this feature only, we be able to predict the seizures. So, and of course it should be wearable, wireless, low power consumption, etc.
Okay, thank you.
Thank you.
Are we finished? Anton, thank you very much.
Thank you.
Okay, I've been asked to point out that lunch will be served in the adaptive learning zone, which is in the main building on the ground floor, and that will be at 12 o'clock.
Is it on now? So I need to talk this normal, is it? Yeah. Is it on now? Yeah, it'll be picking you. Okay. All right.
Spectrum.
Okay. Hello, everyone. My name is Magomed Muradov, and today I'm going to talk about the online monitoring of meat drying process using microwave spectroscopy, which is a part of my PhD research. So due to the complexity and delicate nature of the products in the food industry, the quality control and optimization is quite vital. Specifically in the meat industry, where it has the stringent quality control procedures in place to certify the quality of the products. And the major contributor to the meat quality is the amount of water in it, which is typically about 75%. And the real-time monitoring of, real-time knowledge of its meat's composition, distribution, water holding capacity, and water activity is very important for its quality. And also the moisture content is also a financial contributor, because meat sold by weight, which means higher water content, more profit. Therefore, a way of monitoring it in real life would be significantly beneficial for the industry. So there are a lot of research undertaken in this area using electromagnetic spectrum. However, we focus on the microwaves because it has a number of benefits over these techniques, for instance, namely over infrared, X-ray. So the main advantages of using microwaves is it's non-ionizing, analyze this kind of sensors. So that's why we've been focusing on these type of sensors. So this is the theoretical model of the sensor and also dielectric material or meat sample. So the purpose of this simulation was try to understand a relationship between responses from the sensor and the meat drying process. So what I've done is undertook about 14 simulations by reducing the dielectric properties of this material, which simulates the drying process of the meat. And based on the theory, what I was expecting is to have decrease in frequency shift, because when a meat sample is placed on the sensor, the resonant frequency is supposed to decrease because the wavelength of the signal decreases inside the material. And also, the second change I was expecting is increase of the wavelength of the signal, because when it goes through the meat and because it has high amount of water in it, it absorbs the energy. So as I was expecting, after completing the simulation work, I had these changes, had frequency shift, and also the increase of the wavelength of the signal. So the main question was whether it has a relationship, hopefully a linear relationship with the weight loss. So as you can see, I had very strong linear correlation between the responses from the sensor and also the decrease of the dielectric properties. So based on these results, we constructed the sensor and undertook the experimental work. So to have full control of the curing process, we purchased fresh pork loins from the local slaughterhouse, deboned them, removed the fat, and also sliced them into approximately similar dimensions. Then added salt. We're not really a meat company, so we followed the instructions from the meat company, the amount of salt, and the whole procedure was followed by the instructions from the meat company. So after adding salt to the meat, we vacuum sealed the samples, then placed inside a refrigerator at 4 degrees Celsius during salting and salt equalization, which took 2 weeks. So after completing this stage, we unwrapped the samples and placed them inside our incubation system at 12-14 degrees Celsius, where we had our experimental setup. So what we have in here is 2 digital scales to monitor the weight loss, drip catches, if you will, and also fans to move the excess moisture away from the sensor and the scales. And also to monitor the conditions inside the incubation system, we used temperature and humidity sensor. So all the measurements were taken once per hour, measurements from the scales, measurements from the sensors. The sensors were connected to the vector network analyzer, and the vector network analyzer was connected to the PC. And using LabVIEW software, we gathered all the data. So this is the raw data from the sensor. As you can see, we have similar changes on the spectrum as we had in the theoretical model. Although we didn't have a strong linear relationship between frequency shifts, we found that change of the reflective power at 2.5 gigahertz is highly repeatable and also has a very strong linear relationship between the weight loss of the sample and also the response from the sensor. So based on these results, we used partial least squares regression method to develop the predictive model for the system. And these are the results. So these are predicted versus measured moisture loss values. As you can, not really sure whether you can see or not, R squared equals 0.99, which is very high, very strong relationship. So using these methods, using this predictive model, we are able to predict the weight loss of the samples. And also, this helps us to understand the relationship between the weight loss and the microwaves and use them to develop applications like determining or predicting the water activity in meat or water holding capacity. Okay, that was quick. Okay, so as the main purpose of this was to monitor and to monitor the feasibility study of the to develop microwave sensing system to monitor the weight loss of the sample of the meat samples. As it was demonstrated, we had very good linear relationship between the responses from the sensor and also weight loss of the samples. And the developed predictive model has a great capability to predict weight loss. So the whole experimental work was completed 16 times, and every time we had very high linear relationship between the weight loss of the sample and also changes at that specific frequency, 4.5 gigahertz. So from this stage, we moved to the next part, but I'm not going to include it in this session, which is a prediction of the water activity in the meat samples. Thanks.
Could I take some questions, please? In terms of the meats that you're using, obviously with the different types of meat, there are different weights that are lost at different rates. How many variations have you looked at?
It was between 200 to 350 grams. We had different weights. Well, that not a huge difference, but still we're still getting the same linear relationship at that frequency, that particular frequency.
So whether it's pork or beef or lamb?
Now we're mostly focusing on the pork because the company we're working with, they're curing pork. That's why. What next stage is testing that on the lamb, because there is another company that curing lamb as well. So
Okay.
that's going to be next stage.
Okay, thank you. Any other questions? No? Thank you very much.
That was quick.
Okay, I'd like to welcome our next speaker, which is Patrick Cott. And Patrick will be talking to us about the feasibility of using electromagnetic waves in determining moisture content of building fabrics.
Okay, hello everyone. My name is Patrick Cott and I would like to talk about the feasibility of using electromagnetic waves in determining moisture content of the building fabrics. First of all, I would like to say why it is important to monitor the moisture content between the building fabrics. The moisture content has a huge implication across the structural damages that could be caused into the buildings. First of all, the moisture content could improve the wood deterioration, it could start the fungal growth, or it could work out across the corrosion process between the structure itself. Each building material is able to contain some amount of the water, depending on the location and the type of the material. But if you exceed this level of the water content, you will start having any issues and problems which could be very costly for any refurbishment. As an example, we have Algo Centermal, which is a retail hub in Elliot Lake in Ontario. This building was constructed in 1980s. It was a two-story structure occupied by all commercial units. As well, there was a hotel, and as a future, there was a rooftop parking. There was several water leakage presented and across all the units. They were reported, but there was no work undertaken to service this building. That's why after the time in 2012, the building collapsed. Currently, we do have different types of the meters to determine the moisture content, and some of those units, for example, this one here, it's a pin type moisture meter. We also have some pinless moisture meters, which are a sort of non-destructive methods. But for example, with the pin type moisture meter, this type of the meter has two electrodes on the top of the device, which has to be drilled into the material to take a reading of the moisture content, which is a destructive for the material that we're measuring. On the same size with a pinless moisture meter, it's a non-destructive method, but as a disadvantages of this device is that the penetration depth of the measured material is only up to 2.5 centimeter, where we know the building walls could be much more thicker than 2 centimeters. There is other research undertaken across all the years. There was radiological measurements for the neutron methods and gamma ray methods. Well, as we know, with the gamma ray methods, they could be unhealthy for the people. Also, there is the ultrasonic methods measurements, the electrical measurements, such as the LTCC sensor, the time domain reflectometry, and also we have some physical property measurements. Most of those techniques are destructive to the building fabrics. There's only a minimum amount of the research that is non-destructive, such as the gamma rays, but those methods cannot be commercialized due to the fact that the way they're taking the measurements. As a new approach, I would like to introduce the microwave technology. The presented sensor is in here been built in our research institute. This is the reason why we choose the microwave technology is this sensor will provide us the possibility to undertake the non-destructive measurements, as well as we can make those measurements in a real time. Also, the penetration depth is increased because with our sensor we can penetrate the whole measuring material, which gives us accurate measurements, which I will provide later on during the presentation. Our experimental setup in this case, we use a PC with a graphical user interface developed in the lab view to collect and save all the data. Also, we use some analysis techniques to provide throughout this software as well. The PC is connected to the vector analyzer and connected to our sensor. The sensor is placed in front of the measured material. In the first example, I will talk about the ceiling plasterboard. This material is being placed on the scale to also record and measure the weight loss of the material when the material was soaked in the water across the time. So this is our preliminary results of the drying process for the ceiling plasterboard. As you can see, in the frequency range between 6 GHz to 12 GHz, there is a huge spectrum change in the amplitude while the material is drying off. And all of this is caused by the dielectric properties of the water. When the water has a high dielectric properties, the dielectric properties of overall product will increase, and while the water is evaporates, the dielectric properties will decrease. This is the comparison of the microwave spectroscopy with the weight loss of the material, and as you can see, the R squared in this case is equals to 91, which is a good correlation as well. We've used a prediction algorithm using the partial least squares. Obviously, same as my colleague mentioned, there is a huge relationship between the water loss and the microwave spectroscopy itself. And in this case, the R squared was equals to 0.89. As a second example, we used a totally different material. It was a structurally isolated panel, which was soaked across 24 hours. The experimental setup was exactly the same like in the first test. As we can see, in the same frequency range between 6 GHz and 12 GHz, we have a similar sort of results where the microwave attenuation is changing while the product is drying off. The weight loss and comparison with S1 parameter, which we measured, shows us a higher relationship. The R squared is equals to 0.95 at the frequency of 7.39 GHz, which is as well a good relationship. As a prediction method, again, we've been using the same prediction model, which is the partial least squares. And in this case, the prediction of the moisture content was equals to 0.98, which is, again, very good correlation. For the conclusion, the aim of the research was to determine the moisture content of the building fabrics using the microwave spectroscopy. From the demonstrated results, I would like to show the high linear correlation between the moisture content and the microwave spectroscopy. Also, the predicted model was developed and it's demonstrated as R squared equals to 0.89 in the first experiment and 0.98 in the second experiment, respectively. Okay, thank you very much for your time, and if you have any questions.
please.
You know, you presented some results of the resonant frequencies. You know, you are getting. Thank you. For different materials and a combination of water or moisture contents, there might be a possibility that you might get the same resonant frequencies for different materials. So, what sort of prediction you might be able to do to differentiate between them?
I mean, at the moment we've done we measured the drying off process on different materials and obviously across the different frequency range. So the first point of my, the first step of my research will be to try to choose one single frequency which could give us the similar sort of results. And as you can see on the slides, across the whole spectrum, there was a similar change across the microwave spectroscopy, which shows that at, for example, one frequency, we will be able to have the same results as well.
All right. So in terms of, for example, you might be able to use some advanced algorithms or some processing to still differentiate between different material, even if the same resonant frequencies are achieved?
Yes, I start working on the algorithms to prepare much more accurate algorithm and to determine different changes of the buildings. For example, between different materials, each material has its own unique spectroscopy, which could be used as a key factor of determining what kind of material it is.
Thank you. Cheers.
Are there any other questions, please? Okay, I have one.
Yeah.
In terms of sensitivity of the device, for materials such as timber, which are hygroscopic, is the device sensitive enough to pick up changes in moisture content with changes in relative humidity, say?
All the measurements been taken in the same environmental setup. So also we changed that there was no really effect on the humidity itself, because the way this experiment works, when we have microwave, it's direct. The sensor is very directive. So when we're placing it in front of the material, the microwave will transmit through the material and it will come back to the sensor. And because of the directivity of the sensor itself, it avoids all the other influences.
Okay, thank you very much.
Okay, thank you.
Are we done? Thank you.
Okay, thank you very much.
Okay, ladies and gentlemen, our next speaker is Hannah Wilson, and Hannah will be talking to us about space design and how individual differences influence requirements for the physical environment.
No, it's not on there. Double click. It's not on there.
Where is it?
I don't know. Is it not on? Oh, okay. Oh, I see. Yeah, yeah. Thank you. Yeah. Okay, great. Okay, I've never been very good at technology. Okay, so my name's Hannah Wilson, and I'm going to talk about my research, space design, how individual differences influence requirements for the physical learning environment. So I'm going to focus in on one section of my research, which is individual differences. So all the differences between people and how it affects what workspaces we like to use in higher education learning environments. So first of all, what do I mean about features of the learning environment? So this is anything that makes up the space. So for example, temperature. We're always complaining that it's too hot or too cold in the room. Or is accessibility important? Can we get around the building? Or is natural views or is natural sustainable environment most important for you in your workspace? The design of the learning environments and our space has been found to influence our satisfaction with the environment. For students, a piece of post-occupancy evaluation found that quality of how the environment looked was the only consistent factor in student satisfaction. Not only has it been found to affect student satisfaction, but the quality of the learning environment's also been found to affect academic outcomes. So if students are taught in really nice, really good environments, they're more likely to achieve better. So when I was doing my literature review, I found this really good quote which described what I wanted to do quite well. So most workplaces need a kit of parts to cater for different work styles and to provide a diversity of settings that individuals can self-select to maximise their own productivity. So what this says to me is that each person needs a specific space, a specific environment to work in that suits them to maximise their own working productivity. So, the gap in the knowledge. Currently, there's a lack of understanding how to actually design environments for the students from their perspective. People tend to make assumptions on what students would like out of their environment. And what research that's actually out there rarely actually informs on design processes because it's complicated and very split up. So my research is going to look at the influence of individual differences, so personality and subject cohort, and try and develop a model to design space individually for the students who are going to be using them. So my methodology. I've used a complementary mixed methodology design. I used both surveys and focus groups because I really wanted to explore students' feelings towards the environment, but I also wanted to be able to measure the relationships between the individual differences and factors for the environment. So I conducted the research within students in John Moores between 4 schools, so students from built environment, engineering, art and design and business, because these students also use very different buildings. So we've got the art and design building and we've got Byram Street campus. And I did 10 focus groups with these students as well, discussing the environments they use and what they would change and what they really like. So my focus group findings, first of all, these are all the discussion points around the edge that students discuss. So there's features such as access to technology, suitable classroom space, enough seating. These are all things that students mentioned. These are themes identified from my focus groups. These are the lower level themes, and from that I developed these 6 higher level themes, which are operations, cosmetics, facilities, design and environment, and place. It's not very clear, but all of these arrows here, pointing from these variables, these are all the different schools and how they relate to what features they talked about. So what I identified from the focus groups, that students really discuss different features of the environment. So for example, engineering students really discuss functionality as being really important. Students from art and design and the business school talked about the cleanliness and maintenance of the building being really important to them, but students from the other 2 schools didn't really discuss these features. So what I started to get is a picture of these individual differences affecting what students really find important in their environment. So in the focus groups, we talked about examples of buildings as well, and how this affected their feelings towards the spaces they use. So we talked about Byram Street campus, and students noticed that there's the old and the modern side, and they really like this modern environment being developed. Students from the Redmonds building, they really like this building because it's nice and modern. There's lots of nice open windows. It's really light and open. The art and design building, they liked that they could identify that it was an art and design building, that it was their building, and they had this sense of belonging in the building. And the Henry Cotton building, a student said this is a particularly horrible building, and this was because it was quite dark, and it was a difficult space to get around, as I'm sure quite a lot of you know that building. Okay, so the findings from my survey, I did a factor analysis from all the features in the environment identified from a literature review. And students rated the questionnaire of importance, and I did a factor analysis on all those variables and came up with these factors of the environment. If you can remember from the slide before, they're quite similar from what the students discussed as being important. So we've got social spaces and wayfinding and the layout and the technology. So they're all features that students had discussed and brought up themselves in the focus group discussions. So I carried out a structural equationing model analysis on it, and I have only done the first measurement model, which is this one. But this is all the factors and personality variables, and you can see that there are relationships between them. I have yet to further explore these relationships to really build a model that represents the theory. But I can start to see that there are differences. So personality traits have a relationship with certain features in the environment. So what actual differences are there? How do individuals affect preferences for features in the environment? So as you can see from these charts, students from art and design preferred features like the colour schemes are really important to them, and the aesthetics of design, whereas the other schools didn't rate these as important. So these are features that you think about really focusing upon when designing an art and design building. Also identified there was a difference in personality traits between schools. So for example, students from the built environment scored more highly on the trait of agreeableness. So there's a difference in personality traits between subjects. And also, there was a relationship between these personality traits and features of the learning environment. So people who scored highly on emotional stability preferred features of the window. So if you've got a school that's scores highly on emotional stability, then you'd want to include more access to windows and make it a nice, bright environment for them. So the outcomes of my research, I identified that there are differences. These individual differences do affect preferences for features in the learning environment. So I aim to develop a model that reflects this, so practitioners can design environments suitable for the students who use them. So for example, the environment for art and design students would be different than for engineering students. And I hope this will influence sectional policy, so universities can really be designed for the students who are going to be using them, which will hopefully have an economical impact. Okay, thank you very much for listening. Any questions?
Questions for Hannah, please. Please.
When you were doing the case studies, did you find there was a difference between gender as well as different skills?
Yeah, there was a difference between gender. Yeah, I can't think of anything off the top of my head, but there is.
Why do you think there were such big differences between engineering and non-engineering?
I think it's the type of subject they study. Engineering students are very much focused on the construction of knowledge and using this, which influences the way that they look at the environment and they perceive things. Students from engineering were always talking about how functional the environment is, which I think is quite a good reflection of the way that you approach the subject.
Well, I agree with you. I'm an engineer, but I hate that building.
Yeah, I got that a lot.
Any other questions for Hannah, please? Okay, thank you very much. ladies and gentlemen, can I welcome Christina Unterherzenberger, please? And she's going to talk to us about temporary and complex organisations and the relationship between organisational justice and performance outcomes.
Thank you, Bill. Yeah, good morning, everyone. Bill already mentioned I'm going to talk about organizational justice and the relationship with performance outcomes in the context of construction projects. First of all, I will give you a short background of my research. Then I will show you the conceptual framework which I've developed, the method, and then finally, the most important, the findings